When last we met, we were talking about probability distributions, and just to quickly review, the one distribution that we used over and over that we kept seeing was the number of stocks out of 3 stocks that increased in value. And with this table, we were able to list all the possible values of a random variable x, as well as the probability that x took on each of those values. An alternative way to represent the same exact probability distribution is with a graph. Where the height of each rectangle represents the probability, and you can see by the relative height of these rectangles that 2 is the most likely outcome and 0 is the least likely. We could so the height here would be 0.064, 0.288, etc. But also, if you wanted to, you could calculate the area. And now we can use the area of this rectangle, which is a length of 1 and a height of 288, to represent the probability of that outcome 1. It doesn't really make a lot of sense. It seems like just a lot of extra work until we move on to continuous distributions, where that's the only sensible way to actually represent such a random variable. In case you were thinking 2 ways to represent the same idea is probably one too many, let me give you 2 extra ways. Another way is we can write it out as a formula. If you're a super nerd, this would be your favorite way. In this case, it would be 3 choose x times 0.6 to the x times 1 minus that to the 3 minus x. If you are, however, a normal human being or an executive MBA, this is probably a waste of your time. But you'll see it in a book, so don't be afraid. Another thing we could do is a cumulative distribution, which is actually kind of useful sometimes in certain contexts. Instead of x and the probability that a random variable is equal to that value x, how about less than or equal to? 1, 2, 3, and so this would be 0.064. The chance that x is less than or equal to 0, it could only be 0 or a greater number, so it would be the same. It could also be 0.352, 0.784. The probability that x, the number of stocks that increase in value, is less than or equal to 3, well, that's got to happen. It can never be more than 3 if I only have 3 stocks. And so you can see these are all getting bigger as the numbers get larger. This is just the sum of the probability x equals 0 plus the probability x equals 1. This is that sum plus the probability x equals 2, and this is the sum of probabilities of x equaling 0, 1, 2, or 3. Now you can see that there's a number of different ways to represent the same probability distribution. And I want to see if we can take this notion and use it to describe a different type of probability distribution, one that you may be familiar with. Oh, there it is. This is sometimes called a normal, which is what most textbooks will say. Sometimes Gaussian, after a guy named Gauss, who first characterized it. Sometimes in vernacular you just call it a bell curve or a bell-shaped distribution. I don't know why you would call it a bell curve, except for that it seems to look like a bell. Who knew? When you have a probability distribution like this, we're actually looking at a continuous variable. Something like the length of time it takes you to run a kilometer, or the length of time it takes you to find a parking spot, or the length of time it takes you or your worker to complete a certain task, like checking in a guest at the hotel, or manufacturing a certain part for an airplane or something like that. So a lot of things like time, distance, weights are not easily measured as 0, 1, 2, 3, 4, but they're actually an infinite number of instants in time. So we use something like this to describe a variable that could take on an infinite number of possible values. When we start to talk about probability then, if there's an infinite number of possible values, then the chances of any one of those values occurring is going to be 1 out of infinity, and 1 divided by a number that is ridiculously large is awfully close to 0. So it doesn't make sense to have a table with an infinite number of things, each of which has a probability that's awfully close to 0. So the way we describe a bell curve or a normal distribution is by the probability that the random variable happens to be less than or equal to some number. That is, we use a cumulative distribution. So if I had a bell-shaped curve like this, I'll start to ask questions like, what's the probability it's less than or equal to some value x? And we'll calculate that by calculating the area under the curve, just like we were calculating the area of those rectangles in the distribution that I just showed you. The problem is that to calculate the area of the curve, we have to do a little calculus, and I don't know the shape of this curve. Moreover, there's a whole bunch of different versions of this curve. So we can characterize normal distributions with 2 parameters. Sometimes I'll just use an n, or sometimes you write out normal. If you're lazy, then you'll just do n. And what we do is we characterize it by its mean, the average, and also by the standard deviation or the variance of x. So with these 2 numbers, I can tell you where the center of the bell curve is located, as well as how dispersed this distribution happens to be. Is it really tight in the center, or is it more spread out? So once you know those 2 parameters, you can calculate the area under the curve using some calculus. It's an integral from negative infinity to x of that function, which is 1 over the square root of 2 pi times sigma times e to the negative x minus mu over sigma, and that's all squared, and that's actually 1/2 of that with respect to x. Whew. So I hope your calculus is simple, and you're refreshed, and you're competent in those skills, because it should be relatively easy to do this work. Or if you'd rather, you could just